So welcome back, guys, to the second lesson on waves. And again, I'm sorry you can't be with me, but I do hope you and your family are keeping well during this rather odd time that we're having with the schools closed. So what we're going to look at now very quickly is the oscilloscope. So you might remember that oscilloscopes are, I call them to my juniors, those kind of heart rate monitor machines, where you see a little green dot that travels along the screen and goes beep, beep, beep. Well, in physics, we use one that works at rather higher frequencies, and it has a beam that travels across the screen, and that beam draws a straight line. We then feed a wave into it electrically, and we displace that beam depending on the amplitude of the wave and the displacement of the wave. So the amplitude will stay constant for a given wave, but the displacement will go up and down as the electrical signal goes higher, lower, negative, and back again. Okay, so kind of AC, I suppose. And oscilloscopes are really, really important to scientists for measuring frequencies and time periods. Now, be really careful. An oscilloscope takes a single dot and drags it across the screen in a given amount of time. How long it takes to make each square, to travel across each square, is called the time base. Okay, so if you know that maybe it takes 1 second to do one square, you can see that this wave, the whole wave, takes 2 seconds to make. Yeah, so its time period is 2 seconds. So its frequency is 1/2, is half a hertz. But I've made that one very, very easy. Finally, on this diagram, you cannot see the wavelength here. Okay, this is a time axis, not a distance axis. So be really careful that you don't draw from that peak to that one and say, oh, look at the wavelength. Okay, what you're actually showing, rather cleverly, going from one peak to the next, is the time to make one wave. You're showing the wave's time period. Now, you really do need to know how to use oscilloscopes and how to get frequencies and time periods from them. And of course, yes, you can see the amplitude here, the electrical amplitude of the wave. So what I'd like you to do now, and I'm going to put a link above to it, is I'd like you to head off to another one of my YouTube videos, one that you should look at carefully and understand well, and it's on how to use this machine, a CRO, okay, and I think they still to this day call them CROs, a cathode ray oscilloscope. Just for interest's sake, modern oscilloscopes do not use cathode rays, okay, and later on in the physics course we'll actually look at what cathode rays are and how this machine got its name. So please look at that video now, and when you're done, start this one again, and we'll carry on and do a little bit more work on the wave equation and then on phase of waves. Okay, so I hope you've got a really good understanding now how to use that slightly difficult machine, the cathode ray oscilloscope. So what we're going to look at now is the wave equation. And this is something I hope you'll be very familiar about from GCSE. So, the wave equation. Now this is quite simple, but in fact physicists all over the world have to use this equation to describe how the velocity, frequency and wavelength of a wave are interconnected. So just to make this a little bit quicker, what I'll do is I'll just draw a wiggly wave here. I appreciate that it's got no measurements and it's not drawn on an axis. But I think you know enough about waves now to know that that could be described as very high frequency. And if it's very high frequency, the wavelength is very short. Whereas, if it's a low frequency, the wavelength for the same type of material will be much longer. Okay, so what we note here is that the wavelength, if that gets larger, the frequency gets smaller. So the wavelength is inversely proportional to the frequency. Okay. And if we put a constant in here, so the wavelength must be equal, and I'll just write it in red just to point out that it's a constant, okay, divided by the frequency. And then if we rearrange that for the constant, this constant's quite interesting because it is the velocity of the wave. And I'm going to show you why that is in a minute. So that is the velocity. Being careful to have the velocity in meters per second, the frequency in per seconds in hertz, and the wavelength in meters. So we've now got that the wavelength of any wave is its velocity divided by its frequency. Now, it's interesting that I used c here for a constant because, of course, if it's electromagnetic waves travelling through a vacuum, they go at the speed of light, 3 times 10 to the 8 meters per second. So that c is indeed c. It is indeed the letter that we use for electromagnetic waves. Okay, let's just rearrange it. V equals F lambda. Okay, and I'll squiggle around this. Because whilst that was GCSE, you absolutely must know this formula and you must just completely be conversant with it. Just want to show you something a little bit clever on this. You know that velocity is measured in meters per second. I'll write it like that. Okay. That frequency is measured in per second, so 1 over seconds, and wavelength is measured in meters. Another way of looking at that would be to say this side is in meters seconds to the minus 1, and this side is in seconds to the minus 1, multiplied by meters. So you can see that this equation is dimensionally consistent. That's meters per second, and this is meters per second. Or more importantly, LT, length times time to the minus 1, time to the minus 1, length, so LT to the minus 1. And the constant that you would need to make that work mathematically is the number 1. So there's nothing else needed in here. There isn't a dimensionless constant that's needed. So there we go. GCSE, gosh, wasn't that about a week or 2 weeks' work? Very quickly, formula you must know. Well, c, the speed of an electromagnetic wave, or v, the speed of any other wave, is its frequency times by its wavelength. Right, let's put all this together and do a quick example. Okay, and it's an easy one, but I wanted to do it anyway with you. So let's imagine we've got 600 waves passing a point in 2 minutes. So you look at that specific point and you see a wave go past and another wave go past and another wave go past, and 600 of them pass that point in 2 minutes. Okay, you take a photograph from above, okay, or a video, and you pause it, and you notice from one crest to the next, the wavelength of them is 300 centimeters, so 3 meter rulers. Okay, and I'm going to ask what's their velocity, and then what is their time period. I put time in brackets because what is their period? Okay, so we're going to use V equals F lambda. So we know the wave equation, V equals F lambda. Okay, and I've asked what's their velocity. So their velocity will be their frequency. Okay, 600 waves in 2 minutes. So how many waves per second? Well, 600 divided by 2 minutes, 120 seconds. Okay, and that number is 5. So their frequency will be 5 hertz. Times by their wavelength. I hope you can see what's going on here. Their wavelength is here. It's, centimetres, 3 meters. Yeah, you get kilometres a lot when you deal with radio waves, so you have to be a bit careful. Okay, so their velocity, V comes out at 15 meters per second. Okay, so I hope you found that easy enough. Now, what's their time period? Okay, well, we know from here the frequency was equal to 5 hertz, and we know the time period is equal to 1 over frequency. I'll just say it again. Remember that the time period is in seconds, so this should be in per second. In other words, it should be in hertz, not kilohertz. So the time period, or the period of this wave, is 1 over 5 hertz. So now, this is an important point. I'm often not all that good with my significant figures and things, if you see what I mean. Okay, but I'm just trying to kind of throw out ideas here. I'm not worrying too much about showing how to deal with decimal places and significant figures in this case. But I'm trying to think when you shouldn't. Don't leave answers ever as a fraction. You know I've said this to you in class and you still do it. Don't leave them as a fraction, okay? Because for once I am making the point that if that was a third, it would be 0.3333333333. You'd be quoting your answer to an infinite number of decimal places, an infinite precision, and you don't mean that, okay? So a fifth, yeah, the time period here is 0.2 seconds, okay? I just want to make the point, it's not meant to be a pun, make sure decimal points appear really clearly in your answers, and just watch this little fella. If I'm not careful, I can make it as big as the numbers, and I can make it look like a 5. So there we go, a quick example at using the wave equation, and that should be absolutely fine to get you going for A-level. Okay, so let's move on a little bit and look at wave phase or phase difference. Now, this is really, really important. I probably say that about everything, but this is really important because we're now at A-level and we're going to be looking at waves that meet head-on, okay? And we need to talk about what are the particles doing in those waves and how do they add together, okay? And it's the concept of phase that we need to understand to explain that. So I've put up a sort of FJ definition of phase. It's the difference in displacement, okay, between particles in a wave or in two different waves. Okay, the difference in displacement. Okay, so I'll give you a quick example and then I'll draw what I want to teach. Okay, if you think of a water wave, yeah, if you look at a particle on the crest, that's in a very different place to a particle that's in the trough. The crest one is going to start to drop and the one in the trough is going to start to rise, so they're going in opposite directions. And also, one is very high up. If it's on the top, it has A as the amplitude, and the one down here has minus A. Okay, so there's a difference in their position. In other words, one of them is going to start moving downwards, the other one's going to start moving upwards, so they have what we call a different phase. So let me draw that as a sort of example. So here we go, e.g. Okay, imagine two particles. Now, it might be handy if you imagine these as being in different waves. Okay, so here's a particle in one wave, and here's a particle in a different wave. And you watch those two particles, and you notice that this one is just about to get going upwards. Okay, and this one also is going to start moving upwards as well. In fact, the amplitude doesn't matter. It's just that both are going to start to rise. Okay, rise maybe together. Okay, so we describe these two as being in phase. Yep, moving together. Now, we normally describe this in terms of an angle, and I'll come to that in a minute. But there's basically no difference between their moving. They would move side by side. So we call that a phase angle of 0. Okay. Now, if you go all the way around a circle, you're back to where you started. If you go all the way up and all the way down and back to the axis, you're back where you started. You could have gone through 360 degrees, and that would still put you in phase. Okay, so if you think about it, the crest of one wave and the crest of the next wave, they're not in the same place. We've got a whole wave between them. So there's 360 degrees between them. I'll explain that in a minute. But they're still in phase because they're both going to start to drop. Okay. Now, normally we do this in radians, where there are 2 pi radians in a complete circle. Okay. So pi is about 3.1. So 2 pi is about 6.2. There are 6.2 divisions of the cake in a circle for radians. Okay. And clearly in this case, 0 degrees is no radians, and 360 is the same as saying 2 pi radians. Okay. Now, let's just quickly talk about this, where this angle comes from. Okay. I'll do this with a bit of pen waving. Yeah. 2 objects rotating. Okay. I'll have them rotating correctly anti-clockwise. They're pointing upwards. They're now, I'll do it this way, they're both pointing level, they're both pointing down, and you can see where this is going, okay? They'll be pointing that way, and then the tips of the pens will be vertical again. In other words, if I laid them on top of each other, they would rotate together. They are in phase, there is no angle between them. The amplitudes can be different, okay? But the top of that wave and the top of that wave, rotating together. Okay, one rotation will take a certain amount of time. Okay, so one rotation will give the time period of the wave. The number of rotations per second will give the frequency. But a much easier way to imagine it, and I do this all the time with a small child, okay, is if you have a child on a swing and you're on the swing next to them, if you get pulled back, hopefully you will oscillate in phase. You will go together, maybe not through the same amplitude, but you'll be in phase. Now, what happens if you take the the peak of a wave and the trough of a wave? They're kind of doing this sort of thing. Yep. Okay. So we'll imagine that arrangement. Here's a particle in one wave, just about to move upwards, and in the other wave, or the other part of the wave we're looking at, that particle is just about to move downwards. Okay, so these two are out of phase. It's a very important situation in physics, understanding the phase difference between different points on waves. So my pen example, let's grab 2 pens. One of them sort of up, one of them sort of down. Okay, so as they rotate, the other one will now go up and that one will go down. So if you kind of look at it, they're like that. This one is 180 degrees or pi radians out of phase. So we can put the phase angle between them here. Yep, 180 degrees or pi radians out of phase. And that has a particular name. Because it's quite a nice, one's up, one's down. Okay, other angles would be out of phase, but this is a particular one. It's anti-phase. I don't want to get into too much detail about this, but if you were to add those two, you would always get 0. Well, that's quite interesting. Okay, because you'd have a positive amplitude, and if the other, if it was the thing that was making the wave was the same, or both waves had the same amplitude, then if you added those two together, you get sort of plus half a metre and minus half a metre, you get 0. And you get 0 at all times, which is really interesting. Okay, and we'll deal with that a little bit later on. Then finally, what about this situation? Tricky one to draw. So dot, 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 midpoint. Yep, that particle's there. Just about to get to the top. And this one's just made it to the top, as on its way down. Okay, well, pen waving again. One way of showing that one would be this sort of arrangement, okay, where we've got an angle between them of 90 degrees. It's not very clear from that diagram, but you can sort of see this has got a quarter of the way to move up, okay, and this one is at the top about to move down, okay, so this one has got to go a quarter of the way to get to the top, and this one is at the top about to move down, and if they're the same frequency, they will always remain out of phase, yeah, so they're finding the right colour here, out of phase, but they're out of phase here by 90 degrees or pi by 2 radians. Okay, so I hope you've got a feeling for what phase means. I wasn't going to do this, but I think I will do it very, very quickly. If I draw a wheel here, rotating, this is really sort of heading towards next year, but just suddenly whilst teaching thought I'd do this with you, okay? And if this is a wheel sort of rotating, we tend to rotate anti-clockwise, but don't worry too much about that, okay? If you imagine two spots of paint on the wheel, okay, I'll draw this one as the green dot there, and we'll have the blue one having a slightly lower amplitude. Okay, but I hope you can see that those two will go around together, lined up. They're in phase. You probably don't even need me to draw the anti-phase one. Okay, but here's the green dot, green pen, and the blue dot is 180 degrees out of phase. So the blue dot is sort of here. You'll notice they've got different amplitudes, but that doesn't matter because they're going round at the same rate. Okay, they have the same frequency and same time period. And then this one is an interesting one. Shall we have the blue one at the top? I'm not directly modelling that diagram. I'm just trying to show you the 90-degree angle. Okay, and this one is about to reach the top, so it's here. Put the blue dot in the wrong place, as you probably noticed. Okay, if we stick with the same amplitudes, the blue dot will be there, okay, and the green dot here. And I hope you can see that those two go round together with a 90-degree angle between them at all times, if they are at the same frequency. So now let's have a look at how we can draw this graphically, because I think it will make more sense when you see actual waves. So let's now look at phase graphically, and I think when I draw waves this will make a lot more sense. So drawing skills tested to the limits yet again. So I've got to draw waves that are in phase, in anti-phase, and then 90 degrees out of phase. That'll be the tricky one. Okay, so here's the displacement, S, and the maximum value will be the amplitude. So let me draw a wave. Okay, that hasn't gone too badly, has it? And let's draw a second wave that is in phase with that one. So when every point on this wave is moving up, every point on the other wave is moving up as well. And you'll note that just for interest's sake, I'm drawing this wave at a lower amplitude. That doesn't matter. Okay. I hope you can see that those two waves bob up and bob down. If you look at each particle is either moving up and then moving down in phase with the other one. So this first diagram shows waves that are in phase. Just for interest's sake again, if we pick the peak of this one here, that particle, and the peak of the blue one there, they're in phase, but there's a rotation of 360 degrees, okay? But they're still completely in phase. So let's now look at what we understand by antiphase or outer phase. This is a really important one in physics. Whilst drawing, I'll just waffle a bit. Can you imagine I had some sound where I always played the sound and I always played the sound at the same time in antiphase? Well, every positive amplitude and displacement would cancel out with every negative one and you wouldn't hear anything, okay? Just hinting there at pilots and people who do clay pigeon shooting having noise cancelling headsets. Right, so let's see if we can get the green wave in here. Not too bad. Okay, and then we'll put the blue one in. Doesn't have to be the same amplitude. Is it clear that it doesn't have to be the same amplitude because amplitude is not affected by frequency? Okay, so our other oscillator is doing this. It'd be really cool to see this on an oscilloscope. You'd need two inputs to your oscilloscope, and you could plug into the first input and the second input and actually show those on the screen. And there is actually a button where you can add them. Now, these two are not going to add up to 0 because this one does not have the same amplitude as that one. But imagine it did. Okay? If it had the same amplitude, yeah. And please don't get it into your head that because they're out of phase, the blue one has negative amplitude. No, it doesn't. It has the same amplitude. Okay? It's just in antiphase. Okay? Now, these don't, so they wouldn't add up to make 0. Okay? So these are out of phase, so 180 degrees, pi radians, yep, out of phase. And I know I'm repeating myself, but if this was the case, if this was sound and the blue one was the same amplitude but out of phase by 180 degrees, there would be no sound. Much more interestingly, if these were photons of light, let's not worry too much about the amplitude, okay? If they arrived at a point in space, a single point, where one wave was in the peak stage and one was in the trough stage, and they were the same frequency, I think you could see that those two laser beams would add up and make darkness, which is really weird. And maybe we'll look at that fairly soon. So finally, can I do this one without making a complete mess of it? So what I'm going to do with this one is I'm going to do out of phase, but I'm going to try and get 90 degrees out of phase. So green first. Right, so far so good. Okay, that's the green one. And then it gets a bit tricky with the blue one, but I'll try my best. Okay, so the blue one is going to work like this. When this one's at the top, it's here. Okay. When the green one is at the 0 point, it's here at the top there. I think you get the kind of idea of what's happening now. Okay. This one's at the 0 point, so it'll be there. Okay. So you kind of get reasonably good at trying to draw these. I think I made that point a little bit high. There we go. Down it goes. Up it goes. Down it. Oh, there we go. Okay, not too bad. Bit of a bad start. Okay. Now, you see those and you think, yeah, same frequency, different amplitude, but they're clearly out of phase. Yep. And in this case, they're out of phase by 90 degrees. So 90 degrees or pi by 2 radians. Now, I was going to leave it there, but I just want to show you one little thing just to help you with this. If I just carry this one on this way, just for interest's sake, just as a sort of little dotted line there. Okay, this is more for electrical engineers, but it's still quite interesting. Okay, you can see that an earlier time, yeah, the blue was already at its peak. So we talk about the blue one leading the green one, or the green one lagging the blue one. And let's not worry too much about that, okay? But they have a constant phase relationship. So if these are produced by an oscillator of the same frequency, just a different amplitude, okay, the wheel going round, as it were, okay, they will always travel through space looking like that. They won't catch up with each other, okay? So they've got a constant phase relationship of 90 degrees. So finally, this is a little bit more advanced, but how could we actually calculate the phase or the phase angle between these waves? Okay, well, I guess because it sounds like phase, we use phi. Yep, phi. And the phase angle, it's quite interesting, this. Look at the length between peaks, okay? And if you think about it, okay, if there's a distance between the first wave and the second one, how they're produced, of one wavelength, well, they're in phase, okay? If it's a distance between the peaks of half a wavelength, they're out of phase, yeah? And in this case, you can see we're sort of a quarter difference, okay? There's a quarter of an oscillation between being at the midpoint and being at the low point. Okay, just look at that and see why that's a quarter and not a half. Yeah. Okay, some people struggle with that. You have to get down to this point, up to that point, up to that point, and back again. So it's one of four movements that the wave has to make. So if you think about it, how far along the wave are you compared to the other one? Okay, so how far along is this point here compared to that one? Okay. And how does that compare to the wavelength of the wave? Okay. Well, in the first case, you'll see that there and there, they're in the same place, so that all comes out as 0. In other words, there's a phase angle of 0. You'll notice in this one, between here and here, there's half a wavelength. Okay. So this would be a number, yeah, okay, that you'd be out by, and this would be twice the number, so this would come out as a half. In other words, that is your phase angle, or more importantly, the phase difference between 2 points that you're looking at. Now remember that those 2 points can be on different waves here, or they can be this easy, yeah? You could say, okay, what's the phase between that point on the green wave and that point on the green wave? Okay, well, they're 180 degrees out of phase. The same for the first diagram. The top of the peak here and the bottom of the trough are always, yeah, 180 degrees out of phase. So you can compare the phase angle between points on one wave, or what's really interesting, as I talked about with photons and sound, the phase angle between two waves. So I hope that lesson made sense and you found it useful. Do go back and check the bits that you didn't understand. We're doing really well with our study of waves now, so I'll be making another video soon, and I look forward to seeing you then.